My voice is a little bit off today because Barcelona won last night, and it was a bit stressful. What I'm going to present today is joint work by a bunch of people whose faces and names you can find here, which is effectively the data science team at Letgo. So you may be asking yourself, what is Letgo and what we're going to go through today. So first, I'm going to introduce you to the problem of listing categorization. And then we'll go through the process we more or less followed to solve that problem, which was building a categorization data set, building a taxonomy, starting with an image-based listing categorization system. And then I'll tell you a little bit about what we're planning to do next. So Letgo is, as Santi mentioned, quite a big local two-sided marketplace to exchange used goods, where sellers sell and buyers buy. We're very big in the US and Turkey, but most of our engineering team is here in Barcelona, Spain. So the problem we try to solve is the following. Me, Arnau, I live in Hoboken, New York, and I have this road bike that I want to get rid of. And then Luca, my teammate, lives in Jersey City, also New York, and has been thinking about getting a bike for some time. So what I do is that I post my bike into our platform, and Luca searches for a bike in our platform, and the platform allows us to meet and exchange, in this case, this bicycle. Very simple. Now, one of the key elements of any used goods marketplace is correct categorization of the catalog, right? So when a user, a seller, in this case me, posts a bike, there's a number of steps that happen before that listing, we call the products in our platform listings, goes into our listing catalog. One of these processes is moderation, so making sure that the content is appropriate. Another one of the processes is categorization, so making categorizing that listing into one of the many categories that our buyers search for. Once the listing is in the catalog, then it gets exposed to our buyers through recommender system, search, filter, related listings, etc. So why are we trying to solve that problem using fancy data science as opposed to just asking the sellers during posting time, what's the category of your item? Well, there are in fact two reasons. The first one is that if you've worked on internet-based applications or pretty much any other software product, you will know that as you increase the friction in any process, there's a number of users that drop from that process. This is not actual data, but it's something that we know from every experiment. As you start asking for more details, users stop completing the process. And this is something that we want to avoid because we want to have as many listings as possible. On the other hand, there's another problem, which is that if you ask sellers, they may not give you the appropriate category. One of the reasons they may not do so is because they are adversarial, for instance. So they are trying to, in this case, buy iPhones. And in order to get as much exposure to their listing, which is a service, I buy iPhones, they may place it in the iPhone category. Okay. Another reason is that categories are sometimes complex, and it's not clear to the sellers where they should categorize their item, right? So here, for instance, I posted a listing that was categorized as a car, when in fact it's a car part. This is an engine. So what's the problem we're trying to solve? It's very simply stated. We have a listing that gets posted by a seller. In this case, this is a twin roue stroller. The listing comprises a number of images, a title, a description, price, and perhaps some other metadata. And then we want to build a system, a listing categorizer, that takes this information as an input and outputs the category that this listing should be assigned to. Okay? So many of you in the audience may be thinking, this is just classical supervised learning setup. Okay, easy. Why am I talking about this? Well, it turns out that it's not a simple problem at all. In fact, there are many challenges. The first one, and this is not by order of importance, but by order of my thinking, is the challenge of ambiguity, right? So sometimes users, they will post a listing like this one without much information in the form of title or description. Now, if you just see this image, there's no way for you, for a human or machine or whatever, to decide whether this is someone selling a TV stand, or the TV and the TV stand, the bundle, okay? So these ambiguous situations are quite common. Another problem is that our data is quite noisy because it's user input, and it's user input via a mobile application, right, which has its own caveats. So for instance, here I'm showing an example of a cardigan, right? I mean, depending on your monitor, you may be able to identify a cardigan or not because the image is quite bad quality. Another interesting problem is what we call, and some people in the academy call the open world problem, which is that categories of objects appear and disappear quite regularly. So here I'm showing a specific category that, together with the Google trend on top, which was fidget spinners. So fidget spinners, anyone familiar with what a fidget spinner is? Okay, I discovered them when it's like, what is this thing people are looking for? So they became very popular a couple years ago, and everyone was posting them, and then at some point they kind of disappeared. Okay, so this means that your categories need to be updated at least with demand or with supply. And then finally, as I mentioned earlier, there are adversarial actors, right? So there are people that are trying to cheat your system for their own benefit or just because they want to have fun. So let's start with the first step in building a listing categorization problem, which, as we saw earlier, is a supervised learning problem and hence requires training data. So when we want to train a model, we need training data, and labeled data is typically somewhat expensive, right? So here I did some calculations. So if you want to be able to categorize into 1,500 categories of products, and you want to have a modicum amount of like 1,000 samples per category, you'll need 1.5 million samples. And then if you do the math and include some replication factor to make sure that you correct for the bias or variance of the annotators, you're talking about like, about 200K, above 200K, $200,000 worth of labeling budget. Obviously, if you go to your VP of Finance and say, hey, I have this wonderful new project, give me 200K and I'll solve it, it may not be a good strategy. So another strategy is to kind of like bootstrap your way through the problem, which is exactly what we did, by taking advantage of what we called implicit user feedback, okay? And the idea is very simple. Many people use it. We didn't invent this, but still useful to most people that run a business like ours. So when a user comes to our app and runs a search, in this case, the search query is a road bike, the app returns, hopefully, a number of road bikes if we've done our search and relevance work properly. And the user selects one of them, the one that he or she finds interesting, and contacts them. Perhaps views the item, then contacts the seller, and then eventually transacts. Okay. Now, every time this happens, if we start aggregating across different search sessions, users, etc., what we end up having is, for a very large amount of our products, our listings, the search queries that people used to actually contact the sellers from that listing. So for instance, in this case, we have this Univega mixed road bike that was contacted by 3 different users after searching for the query road bike. Obviously, we don't have just one listing and one query. We may have people searching for Cannondale. We have 4 users that searched for Cannondale and ended up on this listing. We have 1 user that searched for road bike and ended up on this different listing. Now, at this point, you probably already understand where I'm going at. We have tens of millions of different search queries, so different strings of text a month, which means, and we have, I don't know how many millions of search sessions a month, which means we have an amazing trove of data of this type. So it is not all rosy in the implicit user feedback space. And there's a number of challenges. And so I wanted to highlight a few of them. The first one is that you have potential selection bias. What does this mean? So every slide needs to have a Venn, every slide deck needs to have a Venn diagram at least to look smart, I guess. So here's my Venn diagram. This is the set of posted listings, what we call the product supply. This is the set of demand that we call search queries. And the intersection of those two sets are the listings that have implicit annotations. So the ones that I got tagged with some search query after the users interacted with that listing. Now, obviously, if the probability of each class under this sample schema, so the listings that were posted and also were contacted by a search query, is different than the probability of the class in the ensemble of product supply, then I may run into problems, right? Because it may happen that in my training set I have a lot more often a certain type of listings than I actually do have in reality, and this may bias my prediction. So that's one problem. Not necessarily the most difficult one to address. Another problem is what we call uncorrelated label noise. So for some queries, what happens is the following. The user issues a query, sub in this case, which in the US refers to subwoofers 99% of the time. And our algorithm, our search algorithm, correctly returns mostly subwoofers. But if you scroll down enough, you may end up finding something that has nothing to do with a subwoofer, and that happens to pique the interest of the seller. Okay? The user ends up contacting the submariner action figure when in fact her intent was to look for subwoofers. So we call this, obviously, such a contact will create an annotation that's wrong, right? Because that listing here is not a subwoofer, but we have annotated it according to the user as such. Now, this error, this noise, is uncorrelated because the label error depends very weakly on the listing attributes, right? And we can discuss this later because it's a strong statement for very weak evidence. But my point is that the source of this type of label noise, of this type of erroneous annotations, is perhaps curiosity, mistakes due to the UX in the app, or other. It doesn't have to anything to do with the listing itself, okay? Now, the good news is that this type of error is sort of easy to deal with through outlier detection. Not easy, but you can sort of work with it, and I'll talk about one way to deal with it later. The most complex type of error is what we call correlated label noise. And I'm going to give an example here. So here the user searched for Cannondale bike, okay? If the user contacts an actual Cannondale bike afterwards, then no problem, right? The user contacts this Cannondale mountain bike here. We get an annotation for that listing. We can use it later, no problem. Now, in those search results, if you scroll down enough, we may start showing things that are related to Cannondale bikes, but that are not quite Cannondale bikes. And that's a good strategy for search because you want people to stay engaged. Now, the problem is that the user is going to contact these Cannondale shoes after searching for Cannondale bike, and this is going to create an annotation that's wrong. But it's wrong in a specific way. That's a little bit harder to deal with than the previous one. Because in this case, there is a correlation between the attributes of the listing and the noise, the error that the annotation introduced, the seller introduced. The sources of this type of label are not the same as before, where it was a mistake or curiosity. Here it's more perhaps the two listings were similar. They are from the same domain. In this case, those are biking shoes. Or perhaps there's a correlation in the user interest. You know, a person that's interested in bikes is probably interested in biking shoes. Or perhaps you just have errors in your catalog that are systematic. And this is the type of noise that's a lot harder to deal with, and that I'm not actually going to present any way to mitigate it because we're still investigating. Okay? Good news is that none of these issues is a deal breaker for the job that we're trying to do, which is to build a categorization dataset. Now, we have a dataset, we have a plan, and what we need now is a taxonomy. Okay? So, what is a taxonomy? A taxonomy is a very simple concept. Here we have a chair. In a classifieds platform, in Amazon, in any place that sells chairs, there are not one type of chairs, but many. Okay, so here, this is just a sample of the different type of chairs that we have. Adirondack, gaming, feeding. Now, in order to understand the information and to evaluate the model later, we need to actually start thinking about these possible classes in a structure that is easier to understand. And so what we can do is, okay, group all these labels into the chair subcategory in our taxonomy. And similarly, we don't only have chairs, we also have armoires, beds, bed frames, boards, cabinets, etc., which are all part of furniture. Okay? So what I'm describing here is one taxonomy of the many taxonomies that you could decide for your marketplace. Why do we need this? Because in the end, the leaves of this taxonomy, here we have a 3-level taxonomy, are going to be the classes in our classifier. And the tree structure encodes the relationship between the labels. So if we have to build a taxonomy, we need to have a criteria to decide what makes a good taxonomy. So what does make a good taxonomy? So 2 things mostly. The first one is that you want to have good coverage of both supply and demand, right? If you have a very fine-grained, if you cover all possible supply, but you're leaving some demand out, you will never be able to figure out that you need to get some types of products that you currently don't have. On the other hand, it also needs to be user-friendly. So one way to measure how user-friendly it is to minimize user confusion while offering sufficient level of granularity. Here, the chart I show is the result of a UX research experiment, which is called card sorting, where you show random users in focus groups your category tree, and you evaluate how easy it is for them to use it through this confusion matrix type representation. So, okay, we understand more or less how to evaluate a taxonomy given one, but we still don't know how to build one from scratch. Okay. Now, typically, building a taxonomy is a manual process, right? I'm sure there's some papers out there that do it automatically. In the real world, I think it's mostly a manual process. And so that process goes as follows. You have a bucket with class labels, with every possible class that you have been able to imagine. And then you pick one of the possible class labels, here road bike, and then you scan through all the other possible class labels and check with green if those 2 class labels are related. And then you create a group of all the class labels that were related. Okay, in this case, I found road bikes. They are associated with hybrid bikes, BMX bikes, etc. And so I label all these labels in their first level of taxonomy, which is called bikes. Now, if you think of it, so if k is the number of labels in your universe, this is a k square process, right? Even if it's a human who does it, for each one of the labels, it will have to scan k of the other one, so you have to do this in the order of k square times, which is obviously too time consuming if you have 1,500 of them. So the question is, we don't think we can actually replace completely that manual process, but can we help speeding it up? So what I'm going to describe next is a simple strategy to speed up this semi-manual process of creating a taxonomy. So as I described in the first section, we have a way to associate search queries, which now are classes. Let's just call them different types of classes in our different types of categories, to listings. Okay, so this gives me a way to map potential classes to a vector space of dimension n, where n is the number of listings in our platform. Here n could be in the order of many hundreds of millions. So this is a massive fat matrix, fat and short. Now the number of classes is in the order of several thousands. Okay, so now we have this encoding of the classes, and we're just going to do our favorite thing, which is to embed these vectors into a much smaller, lower dimensional space. You can use your favorite embedding algorithm, or to non-negative matrix factorization, latent semantic indexing. It doesn't quite matter. We used word2vec because we tried different options, and that was the one that was working best. And we get this matrix that now is not as fat and short, but a little bit more rectangular. So still fat, but not as fat as before. Or actually, in this case, it would be slim and tall. So we went from fat and short to slim and tall because the dimension of the embedding is a lot smaller than the number of classes. So we're almost done there because now we can just resort to like a beautiful existing clustering algorithm, in this case a hierarchical clustering, to take all these representations of the classes, map them in a way that we can humanly parse it, and that takes us a lot less time than if we had to actually scan each one of the classes against all other. Okay, so there's many ways to interpret this, but one way is that when you have a dendrogram such as this one, you have an ordering of the labels that has semantic sense, and so instead of having to look one against all the others, you have to look at a much smaller range. All right. So we're getting to the final step of the problem, which is actually building. We have the data set, we have the possible labels and their relationships, the taxonomy, and now we want to build the model. So again, a very reasonable question to ask is, why am I going to talk about image-based listing categorization and leave out other possible attributes such as price, text, user attributes, what have you? And there are actually two reasons. So the first one is that at the beginning, in order to create the network effect in our marketplace, so having enough supply, our posting process was just requiring an image. You would take an image, your posting would be processed, we would create an automatic title, we would categorize it for you, moderate it, you didn't have to worry about anything. So very few listings actually had a description. So at that time, all we had to work with was an image, and that's the reason why we started working on image categorization only first. The other reason, which is more relevant currently, where we do have data, more data about most of our listings, is that even if you do have more info, sometimes you want to check whether the information in the text and the image actually match, right? Because it's one way to detect whether the users are trying to trick you. A classical trick in marketplaces is for you to post anything, or actually also in search engines, to post whatever you want to post and do like put iPhone, because everyone knows that iPhones are one of the most searched for listings in the platform, right? So you take your backpack that's about to crumble, like mine, and you post it as an iPhone so that people see it, even if they are not actually looking for it. Okay, so we started with image categorization. And as I mentioned, we did some work to define a taxonomy. We did some work to generate a data set in a cost-effective manner. Then we had to do some pre-processing, because as we saw, there was noise in the labels of our data set, and there's some pre-processing that one wants to do regardless if there's noise or not. There is some training, which we did with, which we use SageMaker for, and I'll get into more details around this in a few slides. And then there's some evaluation and debugging on the performance of our model, which is first done automatically based on a validation set with the noisy labels that we obtained from our dataset generation process. And secondly, manually. And I'll also give a bit more details about what we mean by that, where we use SageMaker Grand Truth. And finally, this cycle, is closed by us, the data scientists, looking at the reports, figuring out what's working, what's not, and updating the taxonomy, the dataset generation, the model, what have you, and iterating over and over. So earlier I mentioned that uncorrelated label noise can be cleaned with outlier detection. Here I just wanted to share with you a technique that proved to be quite effective, which is called isolation forest. And we didn't invent this. I'll put the citation in a second. This is a very simple technique to detect outliers. Okay, so what we do is very simple. We take all the samples for one class, say DSLR cameras. And we project them in one space. Let's suppose that that space is two-dimensional. In fact, it's not. And so this cloud of samples, some of them will be surrounded by many other samples. Some of them will be like the XO there, a lot farther apart from the rest of the samples. Now what isolation forest does is very simple. It says how many trees, so how many cuts in a tree do I need to do in order to uniquely identify each sample, okay? So if you see from the picture already gives an intuition that the number of cuts you need to do, the number of partitions you need to do of your space in order to uniquely isolate an inlier, so a regular sample, is a lot bigger than the number of cuts that you need to do to isolate the outlier XO there. Okay? So then the technique maps this statistic, which is the number of cuts across several trees in the forest, to something called anomaly score, which tends to be centered around some value for the inliers and tends to be away from this, from the mode of this distribution for outliers. So now all you need to do is pick a threshold and declare outliers. As an outlier, anything that's below that threshold. What's cool about it is that this actually works quite well. So here I'm just giving some example of outliers that we detected under the category DSLR cameras. Okay, so just a little note here on why this doesn't work for correlated label noise. For correlated label noise, what would happen is that things that are related to DSLR cameras, like tripods, for instance, would probably be also close to DSLR cameras, so it would be impossible to distinguish them. And there's a good reason why this happens. The takeaway here is that this works for things that are really unrelated to the features that you're looking at. In this case, the things that look like a DSLR camera. So after pre-processing, what we need to do is train the model. And for that, we use the SageMaker platform. How many people have used AWS SageMaker in the room? Okay, so since it's not very many of you, I'll just briefly explain what it does. I think it's very, very useful. So SageMaker is a way for you to allow you as a data scientist to focus on stuff that's not the domain of DevOps as much as possible. Okay. So what SageMaker requires, and here I'm describing one version of it, there's other versions, but this is the one we're using, is one where you define your training algorithm in one of the possible compatible frameworks. In our case, we use MXNet. And you also define the environment on which this training algorithm needs to be executed. In this case, the environment is defined as a Docker file or as a Docker container that contains all the dependencies, libraries, etc. that support the execution of your training script. You also provide an inference script which does the same for the case when your model is already trained and you want to do inference with new images or other. Okay? So you provide this together with a training evaluation data set in S3, and you give it to SageMaker, and SageMaker will run in the infrastructure that you ask it to run it on, and it will produce model artifacts and save them in Amazon S3. So I'm not paid by Amazon, and I want to prove it by enumerating a little bit the pros and cons of this approach. The pros are that it's actually quite easy to use, and yet very flexible, right? So you don't need to marry any of the existing algorithms, etc. You can develop your own architecture. You can do that if you're doing research and have some ideas on how to fine-tune an existing network or other. You can do it. So it's very flexible in that regard. But it's also very powerful because it provides things like endpoint auto-scaling. Right? So for instance, we have a lot of traffic. So our endpoints, our classification endpoints need to handle quite a high number of requests per second under low latency requirements. In a typical scenario, we would have to worry with DevOps and possibly machine learning engineer to tune the thing. But SageMaker gives you the power to abstract yourself away from that and kind of like use all the bells and whistles that the AWS ecosystem provides. Now, on the con side, I want to warn you, there are some tricky things to deal with. First one is that debugging is quite hard because you launch this thing and it gets executed on a VM somewhere that you don't really have access to. All you can see is look at the logs and kind of wonder what's going on. Then on the inference side, so once you've trained the model and you're deploying it as an endpoint, it's not cheap. It's quite expensive. Their SDK has proven to be quite unstable lately. They've broken our code like a couple times in just a month. And integration testing is it's very, very hard, right? Because it's very hard to replicate exactly the environment on which your models, either for training or inference, are being executed. So how are we on time? Good? OK, excellent. So let's move on now to the next step in this virtuous cycle that I described earlier. Of taxonomy, we have the data set, we've preprocessed, we have trained the model, and now it's time to start debugging the model because, as you all know, there's no model that works as is at the first try. So for that, typically what we'll do is we'll define a set of global metrics, precision, recall, accuracy at the different levels of our taxonomy. And we'll also define some local metrics to understand how each class is performing. The insight, though, which is a little bit self-evident, if you've been in this business for a while, is that metrics are very good to measure progress. So they give you a good way to understand whether you're doing better or worse. But they're not as good to help you understand how to fix them. Okay? Of course, there are metrics that help you in that direction. But my point is that most of the times, what you have to do is actually go look at the data and understand what may be causing the mistakes that you're seeing. So this is exactly what we do. In our reports, among other things, we issue a confusion report. And we will find things like this. So these are a set of 10 objects that were labeled as a candle stand, but our model classified as a candle holder. Now, for 99% of humans, these two things are the same, but apparently they are not. Okay, so there's some differences on what a candle stand is and what a candle holder is. And when you see a problem like this, you may start wondering, okay, is it a model capacity problem? Is it that my problem doesn't have enough capacity to actually be able to distinguish those two classes? Especially if you see this type of errors in training and not just on validation. Other types of things you'll notice is that, okay, here I have a bunch of motorcycle tires that were classified as a motorcycle helmet. Oh, wait, these are not motorcycle tires. These are actually motorcycle helmets. So here's an example of items that were actually wrongly labeled in our validation and training data set because of the problems I mentioned earlier. And then another common example is that sometimes there are types of objects that are just simply indistinguishable from the image alone, right? So which one of those is a chessboard? Which one of those is a chess set? Impossible to know until you actually look at what the user said she is selling. There's other potential issues like low sample size. You may have very low sample size for some categories. That's causing increased error, non-disjoint classes, etc. Takeaway is looking at the data gives a lot more information than most metrics one can think of. So all of this evaluation so far has been done with the noisy labels, the labels that we gathered from the user implicit feedback. Now what happens is that this has two problems. The first one is that noisy labels mean that we can't really trust our accuracy metrics, right? So when it tells us it's 80% accurate, it's 80% accurate relative to a label that may be 90% wrong, okay? So that's a problem. And then the other problem is that we don't quite care that much about whether something is absolutely accurately classified. What we care the most about is whether, from a customer perspective, that thing is correctly classified. And those two things are correlated, but not necessarily equal. So to circumvent those two issues, what we want to do is we gather human labels. So we'll have people actually evaluate our model, which seems super easy, right? We take a listing or we take each listing in our data set, we run them through our model, we send it to Amazon SageMaker Ground Truth, which is a labeling service of Amazon, together with our model's prediction, and we let people tell us whether our model is doing the right thing or not. Seems easy. Well, turns out it's not that easy as everything in our data science life, because there's a number of questions that actually matter a lot. The first one is, what do we exactly ask for the evaluator? Do we ask him or her to tell us, is our annotation, is our prediction right or wrong? Or do we ask the person to tell us which one is the correct one? Do we show all the image in the listing? Or do we just show the image that most buyers in the site will see, which is the first one? Do we also show the text? Do we give the users some context with the category tree so that they understand what other possible categories there are? There's many questions. And what happens is that, depending on how you answer them, you get different evaluation results. Here I'm showing the UI that we finally ended up using. That's not important. The important is that you have to think about it and experiment until you hit the nail in the head. All right, so I have 5 minutes left, and which is great because I'm about to wrap up. So I just wanted to share some conclusions on what I've been talking about. The first one is that, in our opinion, this implicit feedback way of generating annotated dataset is quite cost-effective and with problems that one can handle. Another point is that performance evaluation of a model with so many classes is not trivial at all, and you have to think and experiment quite a lot to get it right, which means that you also need to be able to iterate. So the days of building your model on a Jupyter notebook and kind of like versioning by changing the suffix in your notebook file name are over. You have to be a little bit smarter about how to handle versioning and making sure that you can cycle through iterations quickly to just keep tuning all the knobs. And then finally, I believe that SageMaker, and I think Google has something that resembles it, not quite mature yet, but also similar tool, provides quite a good trade-off between flexibility and ease of use. Now, as next steps, we are already working to fix some of the problems, and we have some results. In order to resolve some of the ambiguities, when you have such a deep taxonomy, there are things that are very hard to distinguish. And obviously, using all images as opposed to just one, and using text helps quite a lot. So we're seeing improvement gains in accuracy of 10 points, which is quite significant. And then, as far as how to handle the correlated label noise, there's some work in the literature. We can call it noise-aware models, so models that understand that the labels are not all right. They are quite complex, and we think it's a nice area of a little bit more industrial research to explore. So with this, I wanted to thank you for your attention and ask for questions if there's any.
Hi, I wanted to ask, maybe you can elaborate a bit more on what kind of tools you use for the debugging of those mistakes. How do you inspect what labels are incorrect and so on? Yeah. What's the process?
So our process is very simple right now. There's no fancy like looking at what is it called, salience maps, or like trying to understand what attributes within the image are the ones that are triggering the decision. So we haven't gotten there yet, because so far most of the problems we had to solve were already quite evident by looking at the regular metrics you would look at. So precision recall per class, relationship between sample size and F1 score, for instance, to understand if you're missing samples somewhere, looking at the confusions, and a bunch of like pretty basic things. Yeah, next steps would be also to go a little bit deeper into understanding why some models why some errors are triggered.
Thank you for your talk. And question about coast out problem. What do you do with the pictures or some stuff that is not present in your list? Yeah. How do you start with them?
Yeah, that's a very good question. We don't really have an answer to this. So I think there are ways to detect what may be missing, by looking at queries that are nowhere represented in your data set. So we end up having a map from query to category, right? So you can look for high volume queries that are nowhere in this map, and this will highlight things that you may want to add in your taxonomy. Now, this solves the problem from the demand side. It doesn't quite solve it from the supply side. So honestly, I don't think we have
you select them and do some manual labeling or something like that?
There will be some manual work involved for sure. I can't really think of a way to automate it. The question is, how much can you help that manual work? You know, can you give some indications so the manual work is on a smaller subset of things than what it would be if you don't give any clues?
Hi. Yep.
Yeah.
So I'd be interested a bit in what you actually classify. So is it really just the image, or also are you sending also a bit the main title or the text? And if there are multiple images, are you basically classifying one by one and then aggregating the labels, or a combination of this?
Yeah. So what I described here, this is things that we did some time ago, and this is purely one image-based classification, right? As you are suggesting, and as I mentioned in the next steps, we are already working on multimodal, which for us means grabbing all the images, grabbing the text, price, any other possible feature that may be predictive of the class. For that, we've also tried a variety of things. So for aggregating over several images, there's different ways. You could just do like a simple average. You could do some type of TF-IDF transformation on the representation of the listing as a bag of words of categories. There's different things you can try. They all seem to improve by about the same amount. And then what really makes the difference is looking at the text, because the hardest problems to resolve are the ones that there's just no information in the images to resolve that ambiguity, right? So TV stand TVs are quite good because no matter what picture you take of a TV and a TV stand, you know, it will look like the same. In fact, TVs and TV stands, they do have some differences, because if you're selling the TV, you know, they focus more on the TV and less on the TV stand. So there are ways to do this with object detection and try to understand the scene more generally, etc. But if you just look at the text, it's going to solve your problem a lot faster, right?
Or if there are multiple pictures and one is only of the TV.
Exactly. Yeah.
Hi, thanks for the talk. Have you faced the issue that the taxonomy in one country is different to taxonomy in other country because of cultural reasons?
Yes. So there are so we don't treat it as separate taxonomies. It's just one taxonomy, but some of the classes don't exist in one of the countries, right? For instance, in Turkey, there's like there's a couple of instruments. Baz, I think, is called. Any Turkish in the room? Yeah, Görkem? Saz? Yeah, there's a Saz, and there's another one that, yeah, exactly. And then there's the rosary, that thing with the, well, there's another category that I remember very vividly. So we have them in one taxonomy, only that there won't be any volume for one of the countries. I don't know if that's the right answer, but...
Yeah, at least for our case in the food industry is that, for instance, the taxonomy of Chinese food in Spain is completely different than taxonomy food of Chinese food in China, for instance. So.
Yeah, that sounds like a harder problem.
Yeah.